And we're back. So I actually calculated a different tree because I found one I liked better. But this is an example of what one of the trees in the random forest model looks like. So we start off with how many shots does a team take? The home team take, because it's shots. There's shots dot away down here. That's the away team. If they take more than 6 shots, we continue down the tree. If they take less than 6 shots, we're looking at a pretty high percentage loss, middling draw, and then a low likelihood of winning. Makes sense, right? So all it does is calculate all the games it has in the data set with fewer than 6 shots. And it finds that, let's call it 60% of those end up with the home team losing, about 25% have a draw, and then about 15%, let's say, have the home team winning. But if you have more than 6 shots, then we go down the list. What is the home team's skill? What is that value we calculated with the generalized partial credit model? If it's greater than negative 0.015, then we go down this side of the tree. If it's less or equal to negative 0.015, then we go down this side of the tree. So okay, if it's a team who's bad at home and the away team takes fewer than or equal to 10 shots, you actually have a pretty good chance of winning. You're about, let's call it 55%. 35% chance of a draw, 20% chance of win. That's actually pretty bad math there. So 10% chance of win. If it's greater than 10 shots, then let's look at the number of corner kicks the away team took. If it's less than 3, we're probably looking at a draw. If it's more than 3, you have even likelihood. If your skill is greater than this 0.015, which is a good thing for a home team, we want them to have a high skill score if they're going to win. We look at the number of fouls you suffered. If it's less than or equal to 6, you're probably going to win. If it's greater than 6, then we go to the next step of the tree. We go to the next node. And it's shots on goal by the away team. If it's less than or equal to 5, you almost always win. If it's greater than 5, you're still pretty likely to win, but you add some possibility of a draw there. The random forest model does this as many times as it needs to do. It samples part of the data, it tests it on a percentage of the data, and then it trains it on that part, it tests it on the rest. It then repeats the process again, and goes through this thousands and thousands and thousands of times, creating thousands of these decision trees with every possible value you can think of, every way it can happen. You've got here, so you got 7 cases in this node, 19 in this node, 9, etc. It does this thousands of times and calculates percentage. It takes then each case, runs them through these filters, and figures out which node they end up in. So all it does is it takes all the games and data sets where the home team had fewer than 6 shots. If you did, this is your percentage. If you have greater than 6 shots, it goes down the tree, this is your percentage, or one of these. It applies that math to every case in your data set. That's the basic logic. It's a set of decision trees, but it tries to do as shallow of a tree as it can. As few cases. I mean, if you can predict, all 93 of the cases using only these, 1, 2, 3, 4, 5, 6 variables, and these sort of discrete values, you put them in one of 2 bins, that's pretty cool. That's pretty easy. It's a simple, the logic itself makes a lot of sense. If you take not a lot of shots, you're probably going to lose. If you take a lot of shots, then we look at, are you good? If you're good, then those shots are probably more valuable. If you're not, we need some more information. It's simple. And if you go through the data set, a team who takes this many shots with this skill rating against this many shots away, against this many corner kicks away, you're going to see this percentage likelihood. And you're going to see that in all the cases. It does that with a sample, and then it applies that to the out of sample. It does it again, until it comes up with a relatively stable set of predictions. That's all the random forest model does. It's got a fancy name, but this is pretty much it. It's just got a series of decision trees, which is why it's called a forest. The random part is it randomly picks certain cases. Of the 93, it randomly picks 70 of them or something like that. I think you can specify how many trees are in the model if you choose. But that's what it does. It's a series of decision trees. The logic is fairly simple. The math isn't even that complicated. It's just a matter of humans could never process this in an efficient way. So this is what we're going to use for press, my model. let's go back to our studio, finish up, and I'll show you exactly what we came up with. We are back, and we are back in the wonderful world of our studio here. So I'm going to do the last couple steps here, and actually it's fairly simple. All we're going to do is run the random forest. So I'm going to create an object called rf randomforest.nwsl, and I'm going to store it a random forest model. Again, here's the dependent variable. We're trying to explain the outcome of the game, win, loss, or draw. And then here's the formula we're going to use. The data is the DF Games data set. We don't have these controls because it's a different library. Don't worry about all that, but this is the data set we're going to use. I leave all the options the same. Good machine learning people, I tell my students, I'm teaching you enough to be dangerous here. Good machine learning people, pros at this, will tune their models much better. They also use sample data far bigger than 93 games. This is really 93 games is not nearly enough to train this on, but it's all we have, so it's what I'm doing. I thought about potentially adding in my European soccer database to this, but I think at its core, women's soccer is probably different enough in terms of what affects what. Plus, I have different variables for women's soccer. I don't have the number of corner kicks. I don't have the number of offsides. So I'm losing a couple useful pieces of data here. This is too small for random forest, really, but I think it's important to do, and so I wanted to run it. So you run this. It runs that quickly. It does, all those trees. 10,000 iterations of this in a second. And this is why random forests are so popular. Political folks use this on giant data sets with millions of voters and thousands of variables. And it runs on a powerful computer. It runs very quickly. And this is, your accuracy versus speed trade-off is a huge factor in terms of the random forest model. So it's one of the reasons we like it. It's super fast, and it does a fairly good job of predicting outcomes. But let's see how well it did. So what I'm going to do here is run a table comparing, and it's called a confusion matrix, and comparing the predicted outcome. So in the rf.nwsl, there's a predicted, and it shows the prediction. And then there's the DF Games dollar outcome. So I'm going to compare its predictions to the actual outcome. So I ran my confusion matrix, and it's just a quick table, and you're looking at the values in the diagonal here. If it's a draw, does the model predict the draw? If it's a loss, does the model predict the loss? If it's a win, does the model predict the win? And as you can see, the model predicts losses pretty well. It gets about half the losses correct. Wins, it gets most of the wins correct. Draws, it doesn't do so well, which is interesting because my EPL model does really well in predicting draws, does less on predicting home losses. But we get 45, calculating 34 plus 10 plus 1, we get 45 of the 93 games correct. Let's call that, it's 48% or so. That's not too bad considering we have 3 outcomes and a small data set with limited numbers here. The model gets, about half the games correct. So overall, pretty happy with the outcomes. We'll also want to look at probabilities and do some simulations on the number of points to make sure it's stable. But this is the general idea. Knowing these limited statistics, shots on goal, our GPCM coefficients, fouls, all this stuff, we can predict about half the games correctly. We know nothing else. We know nothing about the players. We know nothing about the weather. We know nothing about momentum and all those other real football men cliches. This is all super quick, top level air conditioner analytics stuff. And we get about half the games right here. My EPL model predicts somewhere around 50% of games correctly too, and it's got a very high correlation. I'm happy where I'm actually leading the scoreboard journalism competition right now in terms of preseason models. The model correlates very well, so if you get half the games correctly, and if the error is sort of randomly distributed among the rest of the games, you're doing pretty well. So ultimately, I'm pretty happy with this model right now. That's the random forest. The next step is going to be to apply individual player data. So for like Orlando, I'm going to need to take their players, apply those statistics to the model, see what I get from there. But this overall is pretty successful. So I will be posting my predictions throughout the season. I think I've got a little bit of time still before the season starts. I'll be doing just like I do with the EPL. I'll be posting weekly predictions. I'll be posting predicted final table, all that good stuff. Giving the NWSL really the statistical treatment it deserves, showing, treating it as seriously as people treat the EPL, because, I'm a big fan of women's soccer, especially how it's going here. I'd love to see a league keep expanding. So hopefully we can, learn a lot about the process. We can learn a lot about small data sets that we have here, not a ton of observations. But life is good. I'm really excited to see how this works. Thank you all for watching. I appreciate you staying with me through. We're pushing 50 minutes right now. Hopefully you all learned a lot. I will continue to post videos as we go. I'll actually probably post a quick bonus video later. But for now, I am Chad Murphy. Follow me on Twitter at SoccerMetric. Like this on YouTube, comment, share it, subscribe, post this on Facebook, post it on Twitter. Please help me get as many eyes on this as I can, especially in the women's soccer world, where I'd love people to be able to see this sort of work. So thank you all very much, and I look forward to speaking with you all throughout the season.